Okay, let's try this instead. So I've selected the data and I've clicked on insert along the top here, and I'm going to use that to sketch a graph. It's bivariate data, so really the most appropriate graph is going to be a scatter plot. And you have to be very careful. In a bivariate data context, we're going to do time series starting at the end of this week. In a bivariate data context, it isn't really appropriate to connect the dots. So please make sure you don't select a graph that connects the dots. In the time series context we do at the end of the week, it is appropriate to connect the dots in most cases, so you will need to. So that's a scatter plot with dots connected. That's one without. So I'm going to choose this scatter plot, and I'm going to make sure there's no connecting at all. You see what happens if you do connect, it makes no sense. So there it is. Now this is really good because it gives us an opportunity to play around with our chart as well. So what I'm going to do, I need to make some changes to this because it's not really great. The first thing is, if you click up in the top corner here, you've got access to chart elements. So you can add axes titles, you can add a chart title, etc., etc. So you can do anything you need to do there, play with the grid lines. What I actually need to do is right click anywhere pretty much, and I'm going to format my axes because my data is too grouped in one corner. Now, typically, you really want to start your graph at 0, 0. As soon as you make a change, you're creating a misleading graph. So, and I'll talk to you a bit more about that in a minute, but ultimately, this represents the fact that my heights vary from there to there, which is actually not a great variance in the whole scheme of things. No one's really short, no one's really tall. But when I zoom this graph into this square here, it's going to look like a massive variance when it's not really. So you've got to be a little bit careful about the misleading element. But we're going to zoom in anyway because it's going to be better for us to actually display and discuss the data and consider the misleading if we need to. So my axis bounds here on my y-axis, I'm going to go from, now my lowest point of data is about 155, so I'm going to go from 150 and up to 200, and that's fine. And I can also set my lines. So I've got my line set as my major lines at 5. If I zoom in enough, my minor lines will pop up at 1, but they won't be labelled on my axis. So I've done that one. Now that I've got the format axis bar up here, I can play around with my axis options straight from there. I've lost my mouse. There it is. It's back. So I'm going to select this, and I'm going to deal with my horizontal ones as well. So I click on my horizontal ones, and I'm going to make my minimum 15 and my maximum 25. That's fine. So now I can see my data better. Now I'm expecting to get data like this because we've measured our handspan and we've measured our height, so they are continuous data points, but everybody in here pretty much measured to the nearest half a centimetre, which has kind of made it look a little bit discrete. There's a column there, there's a column there, there's a column there, there's a column there. So you can expect to see that kind of discrete nature to it, but it still works as a scatter plot. What I'm getting from this, though, is maybe a little bit of positive correlation, but not a great deal. Can everybody see how that's, so there's a lot missing here. Remember we talked about that, and there's a lot missing there. So it's kind of positive correlation, but it's not very strong. What I can do is if I right click on a data point, I get the option to add a trend line. And I'm going to do that. It gives me all these different trend lines I can add, which is great. I just want a linear one. And I'd like to display an R squared value on the chart so I can see that. I'm going to display the equation as well. So this is my linear function. And there's my R squared value. Now this R squared value, remember, is my coefficient of determination. And so I can use that to make the comment, it's quite loose, but I can use that to make the comment that 19% of height can be determined by a handspan. Now, in hindsight, probably I should have swapped my columns around. So I'd expect you to think about that in your PSMT. Probably height is a bit more of a determining factor to handspan than handspan to height, but I actually think they're a little bit co-determining, so it probably doesn't matter too much which way you put them. 19% can be determined by handspan, which is not great. If you take the square root of that, you get your R value, which is your correlation coefficient, and I think it comes out as about, and I'll do that now, but it's about 0.46. So then if we go back and have a look at our scale, let me just do that, 0.1915. If we go back and have a look at our scale, 0.437. That fits into the weak positive correlation. So I have to be careful though. If you know your R squared value and you take a square root, it will give me the positive value. This could be a negative correlation, so I've got to be a little bit careful that I switch it to negative if I need to. But that's where we're at. Everybody comfortable with that so far? I think what we can say is that yes, this I think provides enough evidence for a reason to put the large gloves at the top and the small gloves at the bottom, because it is saying there is more evidence here that taller people have larger handspans than there is evidence that shorter people have larger handspans. It's just not very significant. But I would still take that as enough, because it's not negative correlation, to flip those boxes around if I wanted to. Otherwise, that's pretty much what you're dealing with. And you can make conclusions from there. And those conclusions come based on the strength, based on the positive, negative correlation. But you can also make predictions. So I've got my y equals that, and I can use that to make predictions. It's my a plus bx, but it's in the flipped form, so it's bx plus a. My y-intercept is 129.51. So in context, what does that mean? It means that if you go out and find me somebody who's 129.51 centimetres tall, their handspan will be 0. So it doesn't really work. We can all assume. But you might have a restricted domain there. And this slope says that for every centimetre more on your handspan, you will be about 2.2 centimetres taller. But of course, we've got a pretty bad R squared value, so that's a very loose relationship. Are there any questions on that? So that was pretty much the summary of our activity. What I want to do is I want to show you how you can do this as well on Desmos very quickly, and then I'm going to leave you alone. So if I just flick across here to Desmos, into here. Now you'll probably collect your data in Excel. I personally find Excel a little bit harder to work with, so I'll then move to Desmos. But if you've got your data collected in Excel, copy paste that, go into a Desmos cell here, Control V, and the data will come up. There's my data, there's my information. We zoomed it to fit your data, press Control Z to undo that, but I'm pretty happy with that zoom. So I've got some information there that I can use. What I don't get with Excel now is I don't have a set of axes. So you might need to put that on if you want to use it, because my set of axes is way over there somewhere and way down here, because it stays at 0. Whereas Excel will do a better job of moving the axes, so you've still got that set of axes. I'll let you deal with that. And you've got to make sure you still put arrows on your axes, you have your labels, etc. So you might have to backfill that with Desmos. But otherwise, you've got your data here, and you can do plenty of things with that data, including adding data points and moving them around and playing with it a little bit more geometrically than you can with Excel. If you want to use Desmos, you can also create a regression. The power of Desmos is that you can create a regression in any form you want, whereas Excel is quite restrictive. You've got 5 different types. So if you want to create a regression, just keep in mind, first of all, that if I go to the top of this column, that's called my X1 data, and the top of this column is called my Y1 data. And I'll just go up and show you, because they are really important names in my regression. So I want my regression to be y equals a plus bx. So I'm going to say let y1 be approximately, this is the tilde key, and for most of you, if you're looking at your laptop, it should be shift and then the button below the escape key. Should have a tilde on it, and so it just looks like a single squiggly line, approximately equal to a plus b x1. I do nothing special with that x1, I just type x and then 1. It does it itself. And that recognizes that this tilde thing is saying do a regression in this form, and it will give you all the data. And it will plot the regression on there. So I think that's quite nice and quite powerful. You can vary things. For you guys and with general, we're going to do linear regressions only. Excel does all that. It is quite powerful for the method students who might want to vary some of their regressions, but for you guys, either it really works. With Excel, it's a little bit more fiddly to make sure you get your scales right and get your labels on there. With Desmos, you don't have an axes and you've got to deal with that. So it's kind of, well, whichever one you want. But that's how you do this one. And you'll see here we get the same numbers. And we get the same R value and the same R squared value. So it doesn't make a huge difference. Does anybody have any questions on that? Awesome.